All right, and welcome back. Thank you for joining me for the last video in our systems of linear equations special cases using substitution and the elimination method. This is going to be the last video in this particular series. We're going to go ahead and look at one more problem using the elimination method. Here, we're going to go ahead and strategize again. We see we got both of our equations are in standard form. That does tell us the path of least resistance on this problem is elimination method. In this case, my x is, I got negative x. I could multiply by 3 or negative 3 if I want to use addition method of elimination there and cancel those out. I could do the same thing for the y's. And you know what? I'm going to go ahead and do that. I like to use the elimination method via addition. So I like to get the opposite sign so I don't have to go back and distribute another sign to do subtraction. So I'm going to distribute my sign with this. We're going to distribute in a negative 3. You can choose to modify the first equation, but you would have to use a fraction. I just avoid fractions if at all possible. It's going to make your life easier. I'm going to go ahead and just write this on over here. You're going to see that negative 3 times negative 1 is 3, and 3 times x is 3x. Negative 3 times the invisible 1 in front of the y is negative 3 times that y. And negative 3 times negative 3 is negative 9. All right, looky here. That first equation, I'm just going to copy it on over because there's nothing we need to do to it. It doesn't need to be modified at all. And this is why people prefer the elimination method, because you're about to see how it's quicker than the substitution method. Not always, trust me, not always, but sometimes it is. We're going to add these two lines. All right. Probably maybe better if I use a different color. It's technically what's going on here. A lot of students don't show this part. A lot of teachers don't either. That's technically what's going on. We're adding all of one equation to the other. Negative 3x plus 3x cancels. 3y minus 3y or 3y plus negative 3y. However you want to look at it, cancels. This is 0 plus 0 again. Or 0 minus 0. However you want to look at it. Does not matter. Signs do not affect zeros in that way. Then we have 4 minus 9, and we end up getting negative 5. This one is different than the third problem we did in the series because through elimination method, we found a false statement. 0 will never equal negative 5. Therefore, there is no solution. That means these are parallel lines. They will never intersect. So I'm going to go ahead and grab that graph. And you'll see those lines set side by side, never intersecting. And because the solution to any system is a point of intersection or the points of intersection, and these never intersect, there's no solution. I'm going to write that there. So if you are asked, like on those total concept review chat questions or whatever you want to call it, why there is no solution for parallel lines in a system of linear equation is because the solution to a system of linear equations is either one point or multiple points of intersection. Parallel lines never intersect, therefore no solution exists. All right, your math knowledge has just been patched on solving systems of linear equations using these special cases. In this video, we did focus on the elimination method and achieving no solution algebraically, what that looks like by hand. Thank you so much for your time.